All right, in this last series of more circle examples, we're going to really do some kind of clever things. It's really sort of reverse engineering things, and that is we're going to be given what the principal stresses are in the orientation of those planes, and then from there we're going to figure out a bunch of other stuff, including what in a sense, the original state of stress was, really the stresses that were on the x and y planes, right? So we're given that we have sigma 1, that's the largest or most positive one, is at 2, and that then the smallest or most negative is minus 18. And so that means that we actually have a total range here of 20 on this thing. And we'll come along and we'll see if we can't find a circle on the template that comes close to matching that. Looks like this one does a really good job. There you go. There's your circle. There's your center. Let's label a few things here. This has got a value of 2. That's your sigma 1. Of course, that's tension. Compression is over here, and that value is at 18. That means that with that being a range of 10, then from here to here, this would actually be 8, 10 all the way out for the radius, right? So there to finish that off. All right, so that gives us the basic circle. And it also tells us the radius, which tells us then boom and boom, right there are the maximum shear stresses, right? There's clockwise, there's counterclockwise. So we already know what the maximum shear stress is. It's 10 KSI, plus or minus. You care about the sign of it. Right now, to draw and label the stress block, we got to know a few other things here, and we got to think carefully about what's going on with the principal plane orientation, and so it might help us to go do this down here first before we can come back and really draw the appropriate stress block. Right, and that if you're not quite sure why, that hopefully will emerge as we go through. Right, so to figure out both of these, we really got to know where the x and the y planes are, but we are kind of told that information, right? We're told that the angles to these planes, all right, are those two values respectively. So the angle, this is measured from the x-axis, right? That's the positive or the zero, the datum for the angles, and so 71.6 in real world terms from the x-axis. So that means 71.6 times 2 in more circle world, that's 143.2. That's plus. As we go, and plus means counterclockwise in that world. So if we're going to go from here back, we're going to go the other ways. So clockwise, from here to, so that's 143 degrees to get to, then that's a little over halfway here. That would be what I'd call point A. That's point A, right? So let's go back. Oh, you couldn't see that. There's your point A, right? So we had to go from point A, 71.6 in real world terms, which is 143.2, and we went that way to get our 143.2 degrees. Wow, right? Now there's 90-degree difference there, so that would just take us the rest of the way to get to here. There's your point B. Now, whether it's really on which side of the line it's on, I didn't get a protractor out there. I don't really know yet how that's all going to work. Let's find out. There's 90 degrees, so this angle right here is 53.2, which means, of course, this angle is 90 minus the 53.2, or 36.8. Boy, that's a coinky dinky kind of number, probably a 3, 4, 5 triangle kind of business here. All right, so that's interesting. Now we need to start finding things out like radius, but we know the radius, that's 10. Right? Right, well, that's the radius is 10. And so if we know that that angle is 36.8, then let's take sine. Yeah, it's almost 0.6, yeah, times 10. So that coordinate will be 6 counterclockwise shear stress. And then that makes this is going to be 8. 8 plus the 8 is 16. So it's going to be 16 compression. There's your point A. And if we come down here, what I just discovered was that we've got 16 compression there. That's all KSI, which means we're going to have 16 on this side also. And at 6 counterclockwise, and I can't see that, boom, that means that we are going 6 there, which of course immediately establishes all the other shear stresses because they must pinch together at the corners. Don't need to write that. And we just got to figure out what's going on the normal stress for point B. And let's find out. This is going to be, oh wow, if this base is 8, then that's going to be right here. That's up to 6. So that is 6 up. That's the shear stress. And basically, that means that we ended up with 0 for the normal stress on point B. How about that? That's interesting. Now that only gave us what's going on there. If we want now all the way over to the max shear stress, well, now we know there's your 53.2, and right now that's in more circles terms. So 53.2 divided by 2 means 26.6 here. So that's 2 theta s to get over from A. We're going and spinning a counterclockwise fashion with that plane. So here's then A spinning counterclockwise to get to that plane. I'm going to run that a little bit too long over there. And this is that plane. And on that plane, we've got 8 compression. And we've got counterclockwise again. And that's the magnitude of 10 right there. And once again, that establishes all the others. Again, a little sloppy on creation of the block. And then we'll have 8 right there. How do I know those so fast? Well, that coordinate is 8 compression, 10 counterclockwise. That's this point. And this point, then it goes around. And so that's also going to be 8 compression and 10 now clockwise for that point. And that's how I got this other one. And those 2 of those combined so fast. Right? So let me summarize that for you. Here's your basic Mohrs circle. Right? There's your principal stresses. We're given the angles to the respective ones, which I could go reverse and get to point A, and then I could get the max shear stress easy. I just had to have the right orientation and everything. So I came down here to create that, from which then I could create that one because of now I knew how everything was actually oriented.